Hello and welcome to Honors Function. This is the last lecture in which we will be studying how a function changes. This lecture is about the relative rate of change. Let's begin. So as in the previous lecture, I need a function that I will call f. I need two inputs from my function, so I have to take them in the domain of f, and I'm gonna call y1 f of x1 and y2 f of x2. So we define the relative change of f over the interval x1, x2 as follow. x1, x2, like this. We take the total change, so that's y2 minus y1, and we divide the total change by the initial value, by y1. That's it. That's how I define the relative rate of change. So before we go over some example, let's see how this is different from yesterday's formula. In yesterday's formula, we were dealing with the average rate of change of a function over an interval x1, x2. You remember? What was the formula? It was a total change, but this time it was divided by the total change in the input, x2 minus x1. So this is the total change for every unit of input, while here it's a total change for every unit of the initial output. Let's go over a very simple example to try to understand the difference between the two. So let's look at the price of a stock. I've just checked the Apple share. On October 1st, the share was at $109.58, while on October 30th, the share was at $119.50. Okay? All right, two different prices of the share. So what do we call the average rate of change? The average rate of change of the Apple stock? Well, it would be the difference in the output, y2 minus y1, right? The total change. So in this case, this is y1 and this is y2, right? But you divide that in x2 minus x1. So what is x2 minus x1? Well, it's a change that happens over time, right? So imagine you have a function right here as a function of the time. So of course my example was not very clear, but x2 minus x1 would be how long that change took to happen. How long did it take to happen? So it's 30 days, right? So it would be 119.50 minus 109.58 divided by 30 if my input is number of days. Okay, so what is this equal to? So this is equal to, the total change is $9.92 over 30 days. So it is about $0.33 per day. Okay, so it is the total change in the output per unit of input for every day. Let's now look at the relative change. Okay, so the relative change, what is it? Relative change, what is it? So it's y2 minus y1, but this time I'm going to divide it by y1. So what is that? y2 minus y1 is still $9.92, but this time I'm going to divide by the initial price of the share, 109.58. And if you do that, you're going to find, so it's about 0.0905, etc., etc., etc. Okay? So what does that mean? Well, it's a total change per unit of the initial output, per unit of the initial output. Okay? You divide by the initial output. So it is $0.0905 in change per $1 of input, per $1 of, sorry, not input, of original, of the original price, Okay, So for every $1 in the original price, the change was 0.0905, so about 9 cents. 9 cents for every $1 of the price. Usually we convert that to percent and we say the change was a 9.05%. For every $100 of output, you had a $9.05 change, okay? The bottom, the denominator, is also in dollar. So actually, right here, the dollars could simplify, right? And that's why this doesn't have really a unit, okay? It's 0.05 cents for every dollar of the original price, basically. Okay, I hope this is clear. You will see the application is very, very simple. So, example 1, find the relative change of the function over the interval -3, 2. Well, hey, just apply the formula, right? So it is g of 2, final value, minus g of -3, initial value, divided by the initial value, g of -3. Okay, some students remember the formula as final minus initial divided by initial. It's the same formula. Initial. It describes a percent of increase or decrease. Let's use a calculator here for this. I'm going to show you how to. So the function is 2, -3, and -4. Okay, let me go to my y equal menu and let's enter the function 2 x squared -3 minus 3x -4 minus 4. Here we go. That's my function. I want the relative rate of change between -3 and 2. So now I'm going on my home screen and I'm going to type it. So it is, I want to grab y1, right? So y vars, enter y1. So y1 of 2, all right, if you haven't followed the first time, check it out, minus y1, so it's in vars, you got to go to y vars, function y1, y1 of -3, here we go, right here. And by the way, that gives you the output of a function very nicely and correctly if you enter it correctly, divided by y1 of -3. So y vars, enter y1 of -3. Here we go. And that's going to give me the relative change. Enter. So -1.0869. Okay, actually the 69 becomes a 70 because of the 5 right here. So 0870. You'll see why I'm using so many decimal. -1.0870. So don't forget, this is a percent of increase and decrease. So it's about -108.70%. So between g of -3, when you go from g of -3 to g of -2, you have a decrease of about 108.70%. That's it. That's the relative change between g of -3 and g of -2. Please do number 2. Let's continue. So let's go back to our example of the Apple share right here. We saw that we had a relative change of 9.05%. Okay, that's a relative change. But this relative change happened in 30 days. So now, if you divide the relative change by the difference, the total change in input, so, oops, that should be x2 minus x1 right here, of course. x2 minus x1, right? So if you take this 9.05%, and you divide that by the change in input, so it's 30 days, then you're gonna find about, this is about 0.003, etc., etc., etc. So basically, it's about, and this has a unit, okay, because this is days now. Okay, this is days. So it is about 0.3% per day. Okay, so it means that the Apple share every day increased, it's positive, right? Increased by about 0.3%. And that's how you're going to get to 9.05% at the end of 30 days. Okay, so this is what we call, if you take the relative change and you divide it by the total change input, we call that, so y2 minus y1 over y1 divided by x2 minus x1. This is called the relative rate of change. Okay, when you divide by something with a different unit, you have a rate. It's a relative rate of change. Let's go over another example. All right, the price increase can be significant or inconsequential. In each of the following two cases, find the average change in price and the relative change in price. Express your answer as %. So A Café Mocha, 1F, increasing from $4 to $5.5 over a period of 6 months. Okay, so let's get the average rate of change first, the ARC, average rate of change. So what's the total change? It's $1.50. That's the total change. And it happens in 6 months. So 1.5 divided by 6, and this is $0.25 per month. Okay, $0.25 per month, or actually it's not about, it's exact, sorry, or 25 cents per month. That's the average change. Okay, so your Café Mocha increased by 25 cents per month. How about the average change of the other? In case B right here, what do we have? A cell phone increase from 200 to 240 over a period of 5 months. So the ARC for this one is, what's the total change? $40. $40 in 5 months. So $40 in 5 months, that's $8 a month. $8 per month. Okay? All right, now let's get the relative change. So actually, I want the relative change in price here. Relative change. You know what? I probably meant rate, because the relative change, let's see what the relative change is. Relative change for both. So what do we have for the relative change of the Mocha? The total change is still $1.50, but the price you started with was $4, right? So it's $1.50 divided by 4, while for the other case, we had the total change of $40, but the price you started with was $200. So it's $40 divided by 200. Okay? And these two relative changes are, so this is 0.375, while this is 0.2. So another way of saying that, we had a 37.5% increase, while here we had a 20% increase. Okay, the problem, if I am to compare that, it looks like this is a larger increase, right, than this, because this is 20%, while this is 30.5%. But the problem is that these two increases happen in different time period. Therefore, I really need to compare them. I should use the relative rate of change. So the first one happened in a period of 6 months, right? So 37.5% divided by 6 for the relative rate of change, and 20% divided by 5 for the relative rate of the second. So this is 4% a month. Okay, so the phone had an increase of 4% a month, while the coffee had an increase of 6.25% a month. Okay, so now we can compare. This was a larger increase. Now we can compare. Please do the next example, and let's finish the lesson with another application of the relative change. So the final application of relative change is about the error in measuring. So suppose you are measuring a quantity and you find your measurement is saying that you find XA. This is an approximation, right? This is an approximative value. This is an approximative value. But suppose the exact quantity is X. The exact quantity is X, okay? That's the exact quantity. The absolute error is going to be X minus XA. Well, we don't know which one is larger, so we often put the absolute value right here. This is the absolute error. So this is like the total change. This is exactly like the total change, right? The relative error, relative to what? Relative to the exact value, right? So you take the absolute error, X minus XA, and you divide it by the exact value by x, and that's going to give you the relative error. So it's the error that you're committing for every unit of the exact value. For every unit of the exact value, you are making this error. And of course, if you multiply this by 100, you're going to get the relative percent error, okay? Relative percent error. Let me show you how to use that in math. So in this last example, by the way, you'll have to finish the other cases. In this last example, I'm taking a function, it's a degree 4 polynomial, and I'm asking you, what error do I make if I decide, instead of using this function, instead of using the whole function right here, I'm only using the leading term, okay? So instead of looking at f of 37, instead of looking at f of 37 equals, so negative 2 times 37 to the 4th, plus 13 times 37 cubed, minus 7 times 37 squared, plus 37 minus 9. Well, that's going to take a while if I don't have a calculator to do that. So instead of doing that, I'm saying, hey, listen, I think this is going to be about negative 2 times 37 to the 4th. That's it. That's all. That's all. Okay. I'm forgetting all these terms. What is the error I am making? Okay. All right. So this, of course, is the exact value, right? While this is the approximated value. So let's call this function, let's call g of x. Let's call g of x is negative 2x4. So that's the exact right here. The exact is f of x, right? The approximative function is g. So here is what I want to do basically. I want to do exact value, so f of 37, minus approximate value, g of 37, right? Exact minus approximate, take the absolute value, because I don't care about the sign plus or minus, divided by the exact, f of 37, and I'll multiply this by 100 just to get a percent, and this will give me the error I am making by considering only this part of the function instead of everything else, okay? All right, so I'm going to show you how to do that on your calculator. It's very nifty, and it allows you to quickly answer all of these questions right here, all right? All right, so how do you do that? Check it out. So let's go to the y equals menu. Let's cancel this function right here. And first, I'm going to enter my exact polynomial. So negative 2x to the 4th, here we go, plus 13x cubed, here we go, minus 7x squared, plus x minus 9. That's my exact function. Here is what I used to approximate it, negative 2x to the 4th. That's what I used to approximate it. Okay, and in the third one, I'm going to enter my relative percent error. That's really cool to do it like that, right? So check it out. It's the absolute value of the exact minus the approximative. So the absolute value, this is in numerical, right? So where's my numerical? Math, numerical, you got to go to this menu. Absolute value number 1, here we go, enter. All right, absolute value. Exact minus approximate, so y1 minus y2. Hey, you know where to fetch your y's, right? Vars, y window, y vars, y1, here we go, minus, I don't need to enter of x here, minus y2, vars, y vars, here we go, and y2, number 2, bang, y1 minus y2, divided by the exact, that's y1, vars, y vars, enter, enter, y1, and I want to read that in percent, so times 100. That's it. And my function y3 is my function that will indicate my error. So let's go on the home screen, right here, clear that. Okay, let's check out the error. The first input is 1, so y vars, enter, y3 is my error function, at 1. Okay. Now what is this? Negative 50. Oh, why is it negative? I should put an absolute value around everything, actually. Yeah, right here, I should put an absolute value around everything right here. Where are my notes on error? There should be an absolute value around everything. So right, yeah, an absolute value around this one. That will describe the relative error. I don't care about negative in this case, okay? So let's go back to that. That's a 50% error. 50% error. That means for every 1 unit that is exact, 0.5 unit may be an error. For every 1 exact unit, the approximative is maybe a 0.5 unit error. You may have a 0.5 unit error in the approximation. Okay, 50% error. Let's check out the next one. So the next one is for, so what's the next one? Is it 5? Yeah, 1, 5, 10, 50. Okay, let's check out 5. Alright, so I'm gonna grab the previous one actually. I could retype or I can just grab it like that. And I'm gonna put 5. 5 right here. Okay, what's my error? Oh my gosh, 737%. Well, this is really not good. Okay, you don't want to use negative 2x4 to approximate the function in y1. Let's continue a little bit more. Let's continue a little bit more. So let me grab this one. And now I'm going to enter 10. 10 right here. Okay, what do I have? Negative 1.59. Okay, still not very good. See, I mean, 159% error. These are not very good values. So I want you to do 50, 100, 10,000. Okay, so 50, 100, and 500 and 10,000. Here, let me do one more. Let me do 50. So this right here at 50, what do we have? I think it should get better. It should get better. Let me see. 14% error. You see, this one is a little bit better. I believe if you continue, you're going to find better and better error. Meaning that if this number is small, then you get a really good approximation. If the number is large, you have a terrible, terrible approximation. Okay? All right. Thank you for watching.